Okay, so for inverse trig functions, we have our worksheet here, linked on the agenda, but we're just asked to look at these two statements. Okay, we've been solving lots of things like this. We just spent the last class period solving equations tougher than this, right? But we know that if you look at this, that if the sine of theta is radical 3 over 2, just in the first rotation, you could be at pi over 3, you could be at 2 pi over 3, right? We could take additional rotations. We have an infinite number of solutions here, right? Well, that's a problem because we wanted to find an inverse trig function. We wanted to find a function, get rid of this for right now, called the inverse sine, y equals the inverse sine of x. Now, we talked a little bit about this when we were solving right triangle problems. If you remember, if you knew the ratio, we could use the inverse sine on our calculator. It would find the angle for us, correct? Does that make sense? Okay, what the problem is if we have a function, the basic definition of a function is for each input, you have exactly one output. Okay, well, if you have here, to solve this, we have an infinite number of outputs, right? In this case, we know theta could be pi over 3 plus 2 pi k, where k is contained in the set of integers, or theta could be 2 pi over 3 plus 2 pi k, where k is contained in the set of integers. It's pretty bad C there. Right, so there's an infinite number. That's a problem. Infinite's a lot more than 1, just in the scale of things. So what we're going to need to define this function is we're going to need to put a restriction on the output. We only want to have one output for each input. The reason being, just to kind of quickly describe this, is if we think back to our graph of y equals the sine of x, right? We think back to this y equals the sine of x. We want to think about what this inverse function would look like. And the most basic way to do an inverse function is to let each of the x's become y's and each of the y's become x's. Right? So if we work through this, like we know here's a 0 at 0 and then at pi and at 2 pi, correct? Well, those would move up to here, so this would be 0 and this would be pi and that would be 2 pi. So it would actually look like this if you did this inverse. That is pretty awfully failing the vertical line test, correct? We can't, that's not cool. Like, we can't do that. That's a problem. Now, we do notice that the biggest x value and the smallest x value are 1 and -1, right, when we think about this inverse function. So in terms of our function, y equals the sine inverse of x, right, we know our domain, our input, we know is going to be a ratio, and the output is going to be an angle, right? Because it's an inverse trig function. It's switching it around. That's why we used it to solve for angles and triangles. So what we do to make this actually into a function that passes the vertical line test is we take this graph of sine inverse of x and we get rid of everything that's not, we get rid of all those pieces up there. So we actually just use this little piece of the graph to define it as an inverse function. And if we work that out, we already said the domain is that x is contained between -1 and 1, right? Which makes sense because your sine functions only go from -1 to 1. Okay? But the range, which is the kind of important part that we put a restriction on, will go from, for inverse sine, will go from -pi/2 to +pi/2, or if you want to do that in degrees, it'll go from -90 degrees to +90 degrees. Okay, so what that means is whenever we are asked to evaluate an inverse sine function, like if you're given the inverse sine function in the problem, your answers will have to exist within one of these intervals. Okay, so this, what we did here, is still true, right? Still the sine of theta equals radical 3 over 2. These are all still solutions. Okay, but if we're asked to evaluate what's the inverse sine of radical 3 over 2? So what this is asking is where in the first or fourth quadrant, right, would the sine be radical 3 over 2? And that would be at pi over 3. By the same thinking, the sine inverse of negative radical 3 over 2, well, it's going to be between negative pi over 2 and positive pi over 2. And actually, we have to use a negative to describe it. So we're going to describe this as negative pi over 3. Right? So all the way back to here, we know negative pi over 3 is over here. But you actually describe it as negative. It's wrong to say that it's 5 pi over 3. Even though they're coterminal, the answers have to be within these intervals right here. Okay, that's why we were able to use this with triangles, because they're always, a right triangle always has an acute angle. So it's guaranteed it's going to be in the first quadrant because your ratio is positive. But you'll find inverse sine, and we'll also see that inverse tangent are going to be either in the first or the fourth quadrant. And then we'll look at inverse cosine here too. So let's go. Okay. So this is on your worksheet here, right? So we didn't, I guess we had this inverse cosine piece up here. We could talk about that in a second. But for the inverse sine and inverse tangent for these two functions, right? Your input of both of these is a ratio. Your output will be in quadrants 1 and 4, right? Now, if you notice, if we think back to all students take calculus, we see that sine is positive in the first and negative in the fourth, right? We know that tangent is positive in the first and negative in the fourth. That's one reason that we use those. Plus, it's just kind of, they're close to 0. But the output, your theta, will either be between negative 90 degrees and 90 degrees if you're using degree measure, or it'll be between negative pi over 2 and positive pi over 2 if you're using radian measure. Does that follow for everybody? And that's because of that little graph thing. Okay, tangent's similar. You could look at the graph, but it really doesn't. Pretty much at this point, you just got to remember where it's at. Now, you might hear, for this one, it's not on your worksheet, but the domain for inverse sine is from negative 1 to 1, right? Because we know it's just a ratio, right? It's the opposite over the hypotenuse, or it's the y value on the unit circle. It's not going to be bigger than 1 or smaller than negative 1. If you're ever asked to do the inverse sine of 2, it's undefined. It's a non-real answer. They only work for those. Now, tangents, we know that you could do anything, right? We've had 0 all the way up to an undefined, right? Which approaches infinity. So for this one, the domain, the ratio is that it could be any real number, right? You know, we're going to see things like radical 3 or 1 or radical 3 over 3. But next week, when we use our calculators to do this, we'll see that you can put anything in there and it'll have an inverse tangent. Now, we're kind of leaving out one of our functions here, correct? That'd be cosine. Because of this, we don't use quadrants 1 and 4 with cosine, because cosine's positive in both those places, right? You'd have 2 outputs for 1 input. That wouldn't be good. So for y equals the inverse cosine of x, again, because it is the x value on the unit circle, or it's the ratio of adjacent over hypotenuse, again, you're only going to be able to take the inverse cosine of numbers between negative 1 and positive 1. Right? Anything outside of that is not defined. It's not a real number solution. If your calculator's in imaginary number mode, it'll probably kick a solution out. I'm really not sure what's going on with that. We don't do that. It's not a thing that we do. So here, with this one, the output will be in quadrants 1 and 2. Right? So your outputs are going to be in quadrants 1 or 2, and then the output, theta, must be, between 0 degrees and 180 degrees, or 0 radians and pi radians. So the answer will always exist in the first or the second quadrant. Okay, and again, this happens when you're given one of these functions, right? If we're still solving an equation like we solved yesterday on the delta math activity, you can have an infinite number of solutions, or you might be given a certain set to find the solutions. But if you actually are given an inverse trig function, the answers will have to either be for inverse sine, inverse tangent in the first or fourth quadrant, and for inverse cosine in the first or second quadrant. Okay, so that kind of does the front of our paper here. So let's go ahead to the back and take a look at some of these problems. Okay, if you're following along at home, the worksheet only printed out 3 of the 6 problems you're supposed to try, so never fear, they're up here on the board. But if you haven't tried these, take a minute and try them, but let's see what we get. Okay, so the first one is the inverse sine of negative radical 3 over 2. Now it asks for degrees and radian measure. The degrees are, I don't even think in degrees anymore, I just think in radians, so let's see what we get. I know that radical 3 over 2's happen when I'm up at like a pi over 3 type place, correct? But this is negative, so it's going to move us down to the fourth quadrant. So it's going to be down here, and that's going to be at negative pi over 3, right? So the answer here would be this equals negative pi over 3, or that would be negative 60 degrees. Is that okay with everybody? Now, a little trick here is since sine is either in the first or the fourth quadrant, notice that we said if you had radical 3 over 2 here, it would be pi over 3, correct? If it's negative pi over 3. That happens every time for sine and tangent. So you can, in this situation, and other situations too, but this is the one we're talking about, is if you have an inverse sine or if you have an inverse tangent and they're negative, you can pop the negative out front. Right? So if we did the inverse sine of radical 3 over 2, we'd get pi over 3, but there's a negative there, so it becomes negative pi over 3. So you really only have to know the first quadrant for inverse sines. Now, we have an inverse cosine. That's not the case here, right? This is either first or second quadrant. So we know if we have a cosine of negative 1/2, it's going to have to be in the second quadrant, correct? And I know that inverse cosine, let's see. Well, I know cosines are more x, they're the x values, so that would be up here at 2 pi over 3. Right? Because the cosine at 2 pi over 3 is negative 1/2. So this answer would be 2 pi over 3, or what would that be? See, I actually have to think about these, right? I don't know. It's 120, right? Isn't it?
Yeah.
Yeah, because it's like because you do 180 divided by 3 is 60. 60 times 2 is 120. But radians are easier because they got patterns.
Where is cosine? Are we going to do degree measures all the time?
No, we're hardly ever going to do degree measures. So radians are the wave of the future. Now I think on the delta math assignment, someone asked you for degrees, someone asked you for radians. But see, it's good if you're getting annoyed by having to do degree measures. That means the math people are winning, right? We're converting you to radian measure. So what about the tangent of negative or inverse tangent? Sometimes you'll hear this also. I guess I could have mentioned this. It doesn't happen much anymore, but sometimes this will be arc tangent. Arc tangent means the same thing as inverse tangent. It's kind of old-fashioned. You don't see it much, but if you have an old calculator or an old textbook, it might say arc tangent. I think it had to do with typesetting as much as anything, and not wanting to put an exponent, so they said arc tangent. But where this would be in the first quadrant, correct? Because it's positive. Where in the first quadrant is tangent radical 3 over 3?
60.
Pi over 6, or 30 degrees, which is not really the same thing as 60 at all. But it's half of 60, so yeah. If this is double your answer day, then you nailed it. All right. So what about this one? Cosine inverse of negative radical 3 over 2. Well, which quadrant would this be in first? Second. Yep, second quadrant. So that would be, let's see, cosines are bigger when they're closer to the x-axis, correct? So would that be 5 pi over 6? Or 150? Yeah? All right. How about inverse sine of -1? Well, let's see. If I think about sine, we know it's 0 and 1 and then -1. So it's straight down, correct? Now, there's a lot of ways to write that, but there's only one correct way to write the inverse sine of -1, and that would be negative pi over 2. Right? Negative pi over 2 or negative 90 degrees. If you say 3 pi over 2, it's wrong. That's the catch, right? We have this range restriction because of our domain issues. And inverse cosine of 0? Well, let's see. For cosines, we know it's 1, 0, -1. So that would be up at pi over 2 or 90 degrees. What do you think? Seem mildly believable? Mildly? Somewhat? Okay. Maybe I might have knowledge here. So these are our next three problems, okay? And what you have is you have a sine function inside an inverse sine function or vice versa. Inverse sine inside of a sine function. Sometimes the two things will just cancel, but not always because of that range restriction, right? And sometimes you'll get two different functions, so they're not going to cancel there. But notice here, if you have a sine function here, we're going to work from the inside out. If that's the sine, its input will be an angle, correct? So it's saying if you take the sine of this angle, you'll get some ratio. And then we take the inverse sine of that ratio to get an angle. Right? But here you have a sine function inside. And that would be a typo. No, it's not really. This should be different. That should be like that. That would make a lot more sense, and we'll be able to do it by hand, actually. Otherwise, you can't do it. So this should be, again, this was a little typo here on your worksheet, but it's the inverse sine of 1/2. So 1/2 is a ratio, correct? When we evaluate that, it's going to give us an angle. Then we're going to take the sine of that angle. Here, so with here's pi over 6 an angle or a ratio? What's inside a cosine function, so it must be a angle. Okay? Here is 1/2 an angle or ratio? Ratio because it's inside an inverse sine function. Okay, so as we work through these, what's the sine of pi over 2? 1. And then what's the inverse sine of 1? Pi over 2. So in that case, it canceled out. It'll cancel out when this is in that restricted area. First or fourth quadrant for inverse sine. What's the sine inverse of 1/2? There's a pi. I heard lots of pi's. It's pi over 6. So then we have the sine of pi over 6, which is 1/2. So there, now again, if I would have had it doesn't always work out. Like this one actually always will. Just works. It just cancels out. Let's look at this one. We have tangent inverse of 2 times the cosine of pi over 6. Well, leave the 2. The 2 is just a number, just a multiplier. What is the cosine of pi over 6? Radical 3 over 2. So we get the tangent inverse of 2 times radical 3 over 2. Right. 2 times radical 3 over 2 is radical 3. Right. What's the inverse tangent of radical 3? So it has to be in the first quadrant. But no, pi over 3. It's going to be pi over 3. Does that work? And again, I'm fine if we just do radians. Right, I always think that it's tangent's radical 3 over 3 at pi over 6. There's like 3 plus 3 is 6. And it's just plain old radical 3 at pi over 3 because it's not why it's that way, it's just a happy accident. What's the inverse sine of 1/2?
Pi over 6.
Right, is that pi over 6? So, and then what's the tangent of pi over 6? That would be radical 3 over 3. The one we were just talking about. Okay, so from our next worksheet, we have some different looking problems. What we did last time is we had tangent inverse or cosine inverse of ratios, right? But we knew what the ratio was. We were able to just evaluate it, what we just did. Here, I don't know for what angle we have a tangent ratio of 3, right? Don't know. Never looked it up, you know? Looked it up in a table, but I don't know. But we don't need to. So when you see this type of problem, and I guess you could do it with those other types if you wanted to, it's a little bit extra work though, is this 3 is a ratio, correct? Because it's inside an inverse tangent. So when I evaluate this, bless you, this is going to give me an angle, isn't it? It's going to give me some theta value, right? And this theta value has a tangent of what? 3. So this theta value has a tangent of 3. So what we're going to do here is we're going to draw a triangle. Just a right triangle. We're going to put theta as one of the acute angles. If the tangent is 3, well then the opposite is 3 and the adjacent is 1, isn't it?
Yeah.
Yeah. And then let's see, 1 squared plus 3 squared equals hypotenuse squared. So that would be square root of 10. Right? Pythagorean theorem?
That's math.
Yeah, math. It's a thing we're doing. But it's okay. We're good. So then this will tell us, so what we're actually looking for is what's the cosine of theta? Well, what's the cosine of theta? Can we tell from that picture?
Do triangles, right?
Yeah. It's going to be 1 over radical 10 or radical 10 over 10. That's what you would do there.
I do. Oh, so
Does that work for us? So again, I took the inverse, since tangent inverse of 3 is what I found, that's going to equal some angle, correct? So put theta in a right triangle. Go ahead and draw a tangent of 3 here, right? And then find the hypotenuse. And then we'll find the cosine of theta, which will be 1 over radical 10, and we rationalize it, and it gives us radical 10 over 10. Does that seem believable?
This doesn't feel allowed.
What's that?
This doesn't feel allowed.
Yeah, I know, it's sort of frightening in its beauty. It seems like it should not work. All right, so let's look at this one. This is the same problem, but there's an x in it, which makes it exponentially scarier. No? Okay. So again, x, because it's inside an inverse cosine, this is a ratio, correct? So when I evaluate this, we're going to get some value theta, correct? So can we draw a right triangle? Sure. We'll draw a right triangle. If the cosine is x, that means the adjacent would be x. The hypotenuse is 1. Right, because the cosine is x. Can we use Pythagorean theorem? Yeah, so we get x squared plus b squared equals 1 squared. Or b squared equals 1 minus x squared. And then we go ahead and square root both sides. Is going to be the square root of 1 minus x squared. We're just going to use the principal square root there for now. We'll look later at doing something different with that. So we know that this side here would be radical 1 minus x squared. Do we have enough in, now this was theta still, we didn't label it. Can we find the sine of theta? Sure, well the sine would be 1 minus x squared over 1, which is just radical 1 minus x squared. That's what we can do. So that's it. It looks like it should be really scary, doesn't it, with the, the X in there. So yeah, that's really about all we're going to have time for today. So maybe try. You have a couple more on the front here, and then try those, and then we'll wrap this up.